So in this segment, we're going to look at a variant of the shortest path problem. Instead of looking at the paths from a single source, we may want to compute what's called the all pairs shortest path problem, where as the name says, the goal is to compute the shortest path from every vertex to every other vertex. And this could be useful, for example, in determining routing tables in the internet or something like that, figuring out how packets from one source to one destination should be routed. But you can imagine other uses for the all pairs shortest path problem. So the problem is the following. Given a weighted directed graph G equals VE and a weight function W, we want to find the shortest paths between every pair of vertices U and V. So we will present a very simple solution which also illustrates some of the matrix manipulations you can do on graphs. Because the adjacency matrix of a graph is something that you can use to extract more information about the graph. And that's going to be our first solution. So what we will do is we'll work with a matrix for the graph that looks like the adjacency matrix. So specifically, I'm going to define a matrix A such that the entry ij in A is going to be 0 if I equal to j. So along the diagonal, the entry is going to be 0 all along the diagonal. If there's an edge from I to j, if there's I and j, the entry ij here will be the weight of that edge if there's an edge from I to j. If there are no edges from I to j, the entry will be infinity. So for example, if there's no edge between the vertex 1 and vertex 2, that entry will be infinity. Okay, so that's how the matrix is defined. You may see some similarity to this matrix and something you saw in Dijkstra's algorithm. This is exactly how Dijkstra's algorithm initializes the D array with the I being the source S and J being any vertex. So if you look at the D array, this is exactly this matrix's row corresponding to the source S. But once again, this matrix is defined in this manner. And this matrix has a very simple interpretation. Can you see what it is? Each entry represents the length of the shortest path which uses at most one edge or one hop. So the length of the shortest path from I to j using at most one hop is the entry aij. Why is that? Well, what are all the at most one hop ways of getting from I to j? Well, if I equal to j, you don't have to do anything, and the shortest path is of length 0. So that's why aii equal to 0. Now, if there's an edge from I to j of weight ij, the one hop path length from I to j is exactly that weight ij, and that's why aij equals weight of ij if ij is an edge. And of course, if there is no edge from I to j, there is no one hop path from I to j. So aij equals infinity. So aij represents the length of any path of length at most, and the at most is important, at most 1 from I to j. And I'm going to use the words weight and length here to mean different things just for this section, because length will be the number of edges on the path, but the actual thing we care about is the sum of the weights of the edges on the path. So when we talk about the weight of the path, that's what we want to minimize, but we will look at paths of different lengths in order to do that. So again, aij represents the weight of the shortest path between any pair of vertices using at most one edge, that is of length 1. Now, how do we find the weight of the shortest path using at most 2 edges from I to j? So if there's a path from I to j that uses 2 edges, it must go through some vertex, intermediate vertex k. So the weight of the length 2 path I through k to j is going to be aik plus akj. So that's the length 2 path going through k. And notice one thing about this. I could make k equal to I. One possibility is k equal to I. And then the first term will be aii, which is 0, and the second term will be aij, which is the length of the length of the lowest weight path of at most one hop from I to j. So this actually accounts for both paths of 2 hops and 1 hop, of length 2 and length 1. So if you look at this picture, you want to get from I to j here. I is number 4. I is 4 and j is 3 in this picture. And we're going to let k range over all the possibilities. So in the first example, in the first picture, k is 1. So we could take a path of length, an edge of length 2 from I to k, and then take another edge of length 2 from k to j. That's giving you a total length of 4. Or you could take an edge of length infinity, because there's no edge from 4 to 2, plus an edge of length 3. This path has length infinity. That's not a good path. Or you could take an edge of length 5 and an edge of length 3. In this case, k is equal to j. So that means that we're going from I to j directly on a length 5 edge, and then going from j to j on length 0. That's not so great. The total is 5. We've already seen a total of 4 before. And finally, you could just stay at I, k is equal to I, and then take a path of length, an edge of length 5 from I to j. Again, that's not so great. It's length 5. So the best solution is, in fact, to choose k equal to 1 and take this edge and this edge to get a path of length 4 from I to j. In other words, the lowest weight path with at most 2 hops from I to j is of length 4, and it goes through the vertex 1. So this whole process of computing the shortest length 2, the lowest weight length 2 path from I to j looks like matrix multiplication. We're taking the matrix that we defined A and kind of multiplying it by itself, but it's not multiplication, because normally when we do matrix multiplication, how does it work? We take the row of the first matrix and we take a column of the second matrix. We multiply the corresponding terms in the row and the column, and we add up the products. Here, what we're doing is we're taking a row of the first matrix and a column of the second matrix, but we're adding the corresponding terms and then taking the minimum of the sums. So this is a little bit different, but the structure is the same as matrix multiplication. So if you denote the matrix we get by this kind of multiplication as a squared, so multiplying a by itself is a squared. What does a squared mean? Again, a squared of ij is the length of the shortest weight of a path between I and j that has at most 2 hops in it. A cubed will be at most 3 hops, and so on. And until we can keep on multiplying this by a until we get to a to the n minus 1, which will be the length of a to the n minus 1 of ij will be the length of the shortest path, lowest weight path from I to j that has at most n minus 1 hops in it. In other words, a to the n minus 1 contains all the lowest weight paths which are simple, because any simple path can have at most length n minus 1. A to the n minus 1 of ij is the weight of the shortest path from I to j of length at most n minus 1. Thus, it is the shortest weight simple path from I to j. Could we imagine a non-simple path being shorter? Why would we? So what's a non-simple path? It repeats a vertex. That's what a non-simple path is. That means it went around on a loop. Why would we ever want to do that? Why would we want to loop and come back to a vertex? Well, the only reason we might do that is if that loop has a net negative cost. This is called a negative weight cycle. So if that happens, so for example, if you have a vertex u and a vertex v, and along the way you take a path like this, and along the way there's some vertex and there's a negative weight cycle. So suppose there's a cycle like this that you can take, and it has a total cost. The cycle has a total cost that's negative. Then you could start at u, you could go up to this vertex, and then go as often as you like around this cycle, and then continue on to v if this happens, if there's a negative weight cycle. But if there are negative weight cycles, how do you find it? If there's a negative weight cycle, then as we take this a and quote-unquote multiply it by itself many times, when we get to a to the n, that some diagonal entry we claim becomes negative. So again, a to the n contains the shortest weight, the smallest weight of any n hop path between a vertex and another vertex. So if you look at a to the n of I for some I, and suppose this I is a vertex on this negative weight cycle. So we are assuming a negative weight cycle exists like this. So this is a cycle with many edges on it. So I is some vertex here. So say I is a vertex like this on the cycle, right here. Let's say how do we know that a to the n of I is going to be negative? Well, a to the n minus 1, we would have computed some value to some vertex here. Let's call this just the vertex preceding I, let's call it k. So this is the vertex k here. So we've already computed a length from I to k, and then when we multiply by a again, we're going to take into account the edge ki, and when we add the length of the path from I to k to the weight of the edge ki, we're going to get the total weight of the cycle, which will be negative. We will detect the presence of negative weight cycles if we find that some diagonal entry a to the n I becomes negative. Of course, if there are negative weight cycles, the notion of shortest path is not very well defined. There will be pairs of vertices for which along the path you can take this negative weight cycle infinitely often and get a path of length negative infinity. So in fact, there is no shortest path from one of these vertices to the other, because you can always shorten the path further by taking the negative weight cycle more times. So what the algorithm can hope to do is it can only detect negative weight cycles. When they exist, it cannot return any shortest paths. So this algorithm will actually detect the presence of negative weight cycles, and if they are not there, it'll give you the shortest paths from any vertex to any other vertex. We're doing this different kind of matrix multiplication. We're going to go from a to a squared to a cubed, all the way up to a to the n to detect the presence of negative weight cycles if they exist. Now, multiplying two n by n matrices takes time order n cubed, and you can work this out. It's a very simple a simple algorithm to multiply two matrices. If you write down the program and count its steps, you'll find it's order n cubed. Now, the way we've described the algorithm, we need n matrix multiplications. We've got to go from a to a squared, that's one multiplication, a squared to a cubed, that's a second multiplication, all the way up to n. So we'll need about n multiplications. So this gives us a running time of order n to the fourth. That's not so great. Can we do any better? So yes, instead of sequentially multiplying to go from a to a squared to a cubed and so on, what we can do is we can repeatedly square a. Again, squaring is done in this funny way. It's not exactly standard matrix multiplication. We're going to add corresponding entries instead of multiplying corresponding entries, and we're going to take the minimum instead of adding. But now that you understand what this special kind of multiplication is, we can just square a like this until we get a power of a that's at least n. So we can go from a, we get a squared by multiplying a by itself. From a squared, we can get a to the fourth by multiplying a squared by a squared, which we've already computed. From a to the fourth, a to the eighth, and so on, until we get to a power p, which is between n and 2n. There will always be a power of 2 that's between n and 2n, and we keep on squaring a until we get to this power p. When we do, we have in entry ij, we have the length, we have the shortest weight path with length at most p. And now if there are negative weight cycles, you will see some negatives on the diagonal, and we will give up and say there are negative weight cycles. If there are no negative weight cycles, then the shortest path of length p for any p greater than or equal to n minus 1 is also going to be the shortest path of length n minus 1, because all shortest paths will be simple. So if you allow a path of length at most p, that path will actually be of length at most n minus 1, because it's simple.